and I'll be chairing today's meeting. The technical meeting is sponsored by Middleton Group today. So here's a quick snapshot of the agenda. So for the viewers at the venue, I'll do a quick safety briefing. So if there is an alarm and you hear a whoop whoop sound, we'll have wardens that'll come and escort us back out onto the street the way we came in. We'll turn left onto Goulburn and then left onto Castlereagh, and we'll meet at the assembly point, which is on the bottom left of the screen there. So welcome to the viewers at home. You might be at work, and welcome to the audience at the venue here at the Sydney Masonic Centre. The PWI President, Mark Harris, is on holidays and he sends his apologies, and I'll be standing in for him. The technical meeting subcommittee is myself, Prath, and I work for Sydney Metro. It also consists of Ray Slaviero, who works for the Oricon Group, and he's the technical director and client leader, and also Elaine Human, who is the head of infrastructure at MBM. So thanks to the subcommittee for putting these technical meetings together. So apologies again, as I mentioned, Mark Harris can't make it tonight. Is there any other apologies from the crowd that anyone knows of? No? Okay, so we have some new corporate members. So the Simmel Group, as well as KPMG, the PWI welcomes you. Thanks for joining. I'm sure you'll have a lot to take out of joining the PWI, and we look forward to working with you. So a wrap up of the last technical meeting. The last technical meeting was sponsored by Vossloh, and they talked about floating slab track. It was a very interesting presentation and very relevant. There's so many metros that is happening, construction of metros that is happening across the country. I know for a fact that Sydney Metro are installing FST in 6 months' time at all the new station sites. So that was a very relevant presentation. So what's coming up for the PWI? So the executive breakfast, that's planned for the 12th of May. It will be held at the Parliament House, Strangers Room. So you can get in touch with Steve Normoski if you want more information about that. The winter dinner is also coming up. That's scheduled for the 18th of June, Friday, and bookings are now open. So you can book tables or you can book individual spots. Planning is underway for the annual convention. This is probably one of the biggest events in our calendar year, and it's scheduled for the 29th of October 2021. I know last year we had a blast, especially the networking event, so make sure you book your tickets in for that. A quick update for the memberships. As you can see, we have 2 spare spots in our enhanced memberships, but McConnell Dowell, I think, has grabbed one of those spots as well, so we might only have 1 remaining. So if your company is interested, make sure to reach out to Steve, who's the membership secretary, and the email is on the bottom there of your screen. So the technical meetings for the rest of the year is all booked out. So today's event is going to be sponsored by Middleton Group. The next June meeting is sponsored by WSP. The August meeting, which is combined with the AGM, is sponsored by Arch Artifacts. And then our November meeting is sponsored by Simic Mining. So if you are interested, you can book in for 2022 and you can get in touch with myself or Ray or Elaine. Again, thanks to our enhanced members. We can't do these events without you, so thank you to our platinum sponsors as well as our gold and silver sponsors. Okay, so now onto the technical meeting, sponsored by Middleton Group. So the PWI welcomes Stephen Goh and Andrew Rusak. Stephen Goh is the Principal Engineer and Traction Power Lead for Middleton Group, and Andrew Rusak is the Technical Director for Rail Electrification at Middleton Group. So for viewers at home, we'll try and make this as interactive as possible. You can write your questions online, and for the audience here, you can pass your questions to Elaine, or you can ask directly to our speakers. So Stephen Goh has over 33 years of railway experience spanning all modes of rail systems in all facets of design. He's a specialist in traction power systems, including modelling, design, earthing, bonding and electrolysis, and EMC. Andrew Rusak is a Technical Director for Rail Electrification at Middleton Group. Andrew Rusak has over 20 years of electrified engineering leadership experience within the electricity supply and rail industries, responsible for maintenance and operations, fault response, regulatory management, design, construction. Andrew is a chartered professional engineer and the current national president of the Professionals Australia. So I welcome you, Andrew, if you want to take the stage and commence your presentation.
Thanks, Prath. Great to be here. Middleton Group are very proud to be here and sponsor tonight's event. Just a reminder that Stephen is online, so put your questions in the chat on the way through, and we'll make sure we answer them at the end. I'd just like to start by acknowledging the traditional custodians of the land on which we meet, both here in Sydney, that's the Gadigal people, and those other First Nations people relevant to wherever you might be online around the country, and I pay my respects to elders past, present and emerging. Right, so let us move forward with the presentation. Electrifying our future railways. So this is what we intend to cover today. We won't spend a lot of time on the transition today. We might leave that for a future event, just to leave you hanging. But we'll talk about some of the issues that need to be dealt with, and the way they can be dealt with, and just try and set the scene for those people that might be involved in some of the issues that will need to be dealt with in the future. You've seen enough about us. I won't talk any more about ourselves, but there's something consistent there with middle-aged blokes with no hair. I'm not sure what's going on there, but it's not all the Middleton Group is like that, I can tell you. So just a little bit about Middleton Group and who we are. We are focused in electrical power. That's what we do. We work across those following sectors. Particularly relevant from this presentation's point of view is that we're across transport, renewable energy and power utilities, and you can probably see how those might sort of work together. The key thing for us, we believe we're very passionate about what we do, and we're committed to deliver outstanding technical solutions. I'll come to our vision in a minute, but our vision is to create a sustainable energy future for our communities. And again, you can probably see how that ties things together. So we have teams in Melbourne and here in Sydney. There's about 60 of us at the moment. We do electrical engineering and we do project management based in electrical engineering as well, across those various sectors I mentioned. We're also doing some work in New Zealand, which is great, and it's particularly now that we can actually travel again to New Zealand. It's a wonderful thing. And our aim is to provide that end-to-end power solutions. We specialise in filling the gap between a client's needs and talking to people who can do power things, basically. We have AEO authorisation here in New South Wales, and we're expanding that authorisation into other spaces, but here's the coverage here: E&B, which is earthing and bonding, I should be specific, EMC, which is electromagnetic compatibility, traction power modelling, And as I said, further scope expansions are underway. We're passionate about sharing knowledge to the wider professional community. So we're talking to, I suspect, an audience that's mostly track-based. No, some others. Excellent. It's good to see some electrical people here, not just track-based people. But from my point of view, certainly as a previous history in rail operations space, and as a rail, I call myself a rail engineer. I've got some knowledge of the other disciplines. Bring it together is what a railway is all about. So very important to share knowledge. We love to solve complex problems. We want to use innovation and use new technologies, build our relationships with our stakeholders, and we take pride in knowing, how to get things through government, etc. So with that background done, I will hand over to Stephen, who will begin by taking us through a bit of background about 25 kV systems. So we need to give you a bit of this first before we talk about some of the issues. So Stephen, I'll hand over to you.
Thank you, Andrew. Some of you may have heard some of these presentations before. Hopefully there's something new for you this time as well. Did you know that there are many types of 25 kV AC systems? Today, I will give an overview of 5 types. The first 3, rail return, booster transformer and auto transformers, are transformer-based systems which are tried and tested, each with pros and cons. The last 2 are power electronic-based static frequency converter systems, which are relatively new technology but are gaining popularity. Next slide. This is a very simple rail return system or RR system. And it uses the overhead line consisting of contact wire and wire carry current from the station to the train, and it uses the running rail to return current to leakage current, using leakage current, not stray current. I reserve stray current for DC system. 50 leakage current can be high, up to 20%, depending on your track form insulation resistance level. If you have very good track insulation, you will minimize your leakage. And the EMC performance is not as good compared with booster transformer and auto transformer systems. Next slide, please. Next slide. Andrew.
Stephen, you should have the booster. You have the booster transformer slide in front of you.
This is a booster transformer, a BT system. Yes, you can see it. Is it on the screen? Is on the screen.
Yes, Stephen, you've got
this is a booster transformer or the BT system with a plug wire at the top there, which is red. And right, okay. The BTs, booster transformers, are typically spaced 3.2 kilometers apart, are often mounted on the overhead line structure, and that means it doesn't occupy space on the ground. And the name BT is actually misleading. It does not boost the line voltage at all. It actually depreciates the voltage at each BT location, because the BTs are actually connected in series with the overhead line impedance between the feeder station and the train. So what are the pros of this system? 50 Hertz leakage current is now confined and controlled. So the action of the BT actually pulls the rail current and the 50 hertz current, 50 hertz leakage current out of the earth to the aerial return conductor via the midpoint connector, those blue lines, vertical lines, and return it to the feeder station via the secondary winding of the booster transformers. The current in the return conductor and the overhead line produce opposing magnetic fields and cancel each other, thereby improving the EMC performance, and is better than the rail return system. Now, what is the con? Are the cons? BT system obviously is more expensive than rail return system, as it requires additional equipment, booster transformers, midpoint connector, return conductor, and bypass switches for the air gaps as well, in case you want to bypass a booster transformer. And of course, there's more components for maintenance people. Next slide. This is an auto transformer, or the AT system. AT system distributes power at 50 kV, but train draws power at 25 kV between the contact wire and rails. There's also an additional conductor called auto transformer feeder, short for ATF, and in France it's called negative feeders. ATs are installed typically at 10 kilometers apart along the lines, and they're connecting the positive 25 kV and minus 25 kV, and the midpoint, the center point, is connected to earth and to rails. Now, what are the pros for this system? 50 hertz leakage current is confined and controlled. The action of the AT pulls the rail current and the 50 hertz leakage current out of the earth to return to the center tap of the auto transformers. The opposing current flowing in each subsections, producing opposing cancelling magnetic fields, resulting in EMC performance that is superior to both the rail return and the booster transformer systems. Now, what are the cons? Again, it is more expensive than booster and return conductor system with additional equipment. So you have auto transformers at 10 kilometer interval, and they need switchgear and also LAN as well along the alignment for the auto transformer station. Obviously, again, there's more maintenance for the equipment. Next slide, please. Now we come to a new technology here, static frequency converter. So using rail return, this system is 1 times 25 kV AC using rail as return conductor. So in Australia and the UK, we have 3-phase high voltage going in at 50 hertz and 1-phase, single phase, 25 kV out, also at 50 hertz. And of course, in countries like Germany, Austria, Switzerland, Norway, and Sweden, they have 15 kV out and 16.7 hertz instead of 50 hertz. So these SFCs are installed along the line with no neutral section required. You can actually tune the output of the SFC to be all in phase, so you do not require a neutral section. So the pros of this system is 50 hertz leakage current is partially controlled. It's better than rail return system because the return, your current will come from several SFC to the train from both directions, and they have to return to where they come from. and so therefore it's actually better than the rail return system. EMC performance is also better than the classic rail return system, and as you can see, this particular train is fed from both direction or 2 or 3 adjacent static frequency converters. SFC requires smaller lens size than transformer-based feeder stations. So the high voltage balancers are not required because we are taking 3-phase supply. The supply is already balanced, so you don't need to balance it. So there's no additional land required or no additional equipment required to balance the 3-phase supply. And of course, as I mentioned earlier, no neutral section required. So SFC can operate in phase. So it's better for recycling of regenerative braking energy. So the energy can flow anywhere it likes to a motoring train from a braking train. And so what are the cons? Now, traction transformer-based system allows an overload of say 150% up to 2 hours and 300% up to 5 minutes. Static frequency converter, you don't have that. You have to pay for it if you want extra. So that's why sometimes you see non-standard size units being distributed to certain projects. And for ABB, they come in 20 MVAs per unit, so you can have as many as you need to bolt them together in parallel to form one SFC feeder station. And GE, they come in 15 MVA per unit, and Siemens 12 MVA per unit. And SFC have shorter design line of something like 30 to 40 years compared with transformers based systems. And also, don't forget, the cooling system needs to be rebuilt or replaced every 15 years. See the Lego looking thing sitting on top of the green block, that's your cooling system. So that will need to be replaced or rebuilt every 15 years. And what it means is your SFC will need to be shut down. So if you're adopting this solution, make sure you have enough SFC on the system to allow for N-1 situation and still allow the train operator to operate the full service under N-1. And also under N-2, when you have 2 units down, you are still required to provide enough power for the operator to operate a reduced service acceptable and negotiable with the train operator. Now, SFCs by different manufacturers are not interchangeable, and at the moment, I believe they're not interchangeable. So that means that once you've chosen one, you're stuck with them for life. So bear that in mind. Unlike transformers, you can buy it from any manufacturer to replace it. Okay, next. Oh yeah, we have several units already operational in Queensland and 2 units in UK as well on the East Coast Main Line near Doncaster. And this is the SFC 2x 25 kV system using auto transformers. Some of the auto transformer between the SFCs are missing. So what it means is you have 50 kV transmission and you have auto transformer stations in between. So that means you can feed much further than the 1x 25 kV system. So it has all the benefits of the classic auto transformer systems, and I reckon the EMC is as good or better than the classic AT system, as train current is actually fed from both directions, so you don't have the full current coming from one direction. And again, all the benefits of the 1x 25 kV are there. So SFC requires, it takes up smaller land size, voltage balancer not required, no neutral section, and of course it's got all the cons of the single phase 1x25 kV system as well, as I mentioned earlier. Next slide, please. Now this slide is just to show you what to expect and what you mustn't touch, what you can touch. So on the left-hand side, very left-hand side, you have the auto transformer system. So in addition to your contact wire and catenary wire and the running rails, and the earth wire may not be in the right position. Some of the earth wire are right at the top of the pole to act as a lightning. When lightning strikes, it catches lightning as well. So the auto transformer feeder -25 kV, it normally sits on top, and preferably sit facing inward. So on a track, especially in a platform, you don't want the live wire to be falling onto the platform. In the middle is actually a hybrid. So you got the contact wire, catenary, running rails, and then earth wire. Oh yes, the earth wire is the bonded to the running rails, and the structure is actually used as like a mini earth rod along the track to give you your distributed earthing system. And for the booster transformer, there's a return conductor up there as well. Now on the right hand side is what you would use in a tunnel section, using ROCB. Sometimes you might hear somebody's a conductor bar, conductor beam. In Hong Kong, they've got a conductor rail. So they're all the same thing, just different names. So it uses an aluminium extrusion, which is hollow in the middle, and the contact wire, copper, hard-drawn copper contact wire is clipped onto the bottom of it. Your pantograph is actually making contact with a contact wire, not the aluminium. So you can see the insulator, between the RCB and the support, and there's also an earth wire running along as well. Next slide. Right. Now I pass you back to Andrew to talk about some pros and cons of AC systems and further pros and cons. Over to you, Andrew.
Thank you, Stephen. These pros and cons will help to explain some of the interface issues. So Stephen talked about some of the specific benefits of the different types of system, but overall, 25 kV versus 1500 volt systems, lower line current. There's a reason why high amounts of power are transmitted at high voltages. You get less current, the P equals V times I equation. So if you've got less current that's required to be supported in the conductors, you've got less weight to be supported by the structures because you've got smaller conductors, and that will apply the wind loading, not just the static loading. That's a good thing. Reduced traction currents in the overhead system means generally reduced conductor temperatures, which means you've got less chances of wire sag and dewirement, and annealing of copper conductors. That's a good thing. Good thing about AC systems is electrolysis is limited. AC electrolysis is sort of known, but the effects of AC electrolysis are very much less, less than 5% what they are for a DC system. And just a reminder that driven electrolysis via the stray currents that escape basically from the return rail system can drive corrosion rates of up to 9.2 kilograms per amp per year. So you can imagine if you've got a few hundred amps flowing through the return path through third party or rail assets, you can get a lot of steel disappearing very quickly into nothing. So that's another positive. Because of the much lower currents, there's a lot less losses. Also, there's less transformation points. So there's less feeder stations than there is substations in the DC system, which is actually the next point. But it also contributes to the lower, the better energy, sorry, the lower energy bill, if you like, from an AC 25 kV system. Just for example, some work we did recently showed that the rail system in Melbourne, the new system from Sunbury to Pakenham, which will be through the new tunnel, the two lines will be joined. It's about 100 kilometres. If that was run at 25 kV versus 1500, the savings would be roughly, this is energy savings, would be roughly enough to run 30 domestic dwellings for 1 year. That's just the difference in the traction power systems, nothing else. No train timetables, 30 dwellings for 1 year. So it's a significant amount of energy that you can reduce. So that's another plus. And as I mentioned, fewer substations, transformation points, means lower cost as far as the supply side goes. What also means that there's a lot less land use. But this will be slightly shown in the next slide to be also slightly negative. But so there's less substations. Each of those substations, though, here's some cons, are slightly bigger. So instead of having a 10 by 20 metre substation, but lots of them, you'll have a few, say 50 by 50 metre substations. They can be made fairly compact. SFCs make them more compact, but you've got so a lot less substations, 2 or 3 on a 25 kV system versus 30 or more on a DC system. So the difference is a few big ones versus trackside smaller ones, but generally the pros there outweigh the cons overall in land use. Stephen mentioned neutral sections. So in the traditional 25 kV system, you've got an out of phase issue with transformers. That means there's actually a little bit of dead section in the overhead where the train has to run through. More maintenance. It doesn't really affect train operations as long as you put your neutral sections in the right place. Like you wouldn't put your neutral section right at a signal. That would be rather crazy. So as long as the system's designed properly, it's not an issue. You do get momentary dips in the auxiliary system, so your air conditioning might go out, etc. At least the compressor would. So an SSC system, as Stephen mentioned, fixes that problem. Another thing is that you need usually to connect a 25 kV system to a strong power supply. That usually means a transmission grade power supply connection at 110, 132, 220, 275 kV, that sort of thing. Crossrail, I think, was connected at 400 kV near the City of London. The SFC, though, really helps with that. So it is a negative in the sense of traditional AC, 25 kV AC power supply connection, but SFC allows that connection to be done at a lot lower voltage. Reasons for that are mainly load balancing. It's a balanced 3-phase supply. And as you saw on the previous slides, you can run SFCs in parallel like a DC railway, lots of in-feed points, so they can be smaller capacity each. Okay, so let's talk about some of the issues at the interfaces. Look at the Sydney system. Presently, this is the system as it stands with all 1500 volt railways. There's a tram in there somewhere as well. The new metro is 1500. Future system with additional metro systems, as noted here with the dotted lines, potentially could be 25 kV powered systems. So that means that at the interface stations between an existing 1500 volt DC traction power system and a 25 kV AC system, there could be some issues we have to deal with. So there's potentially 8 or 9 interface points on the system. So let's look at some of the issues and what they might be. So I'll just flick back. I'll just note that I think it's very good that the Electrifing, let me find the right button here. The Electrifing station is to be named Bradfield. It's good to see infrastructure that's being built named after engineers. Wonderful thing. Should be more of it. So let's have a look at the issues. So here's a bit of a list, and I'll summarise with a key takeaway here. So because traditionally 25 kV systems, 1500 volt systems use slightly different earthing arrangements. For example, 25 kV, as Stephen pointed out, has a connection to ground. DC rail systems traditionally don't, because that doesn't help you with stray current electrolysis. It tends to contribute to it. You want to isolate your tracks, your rails from the ground. Two effectively slightly competing earthing systems. So at the interface, you need to put forward a combined earthing and bonding strategy that works for both. And that means you're managing the touch voltages that come with the general operation of the railway. Touch is where people can actually touch assets at different potential, and also under fault conditions. Also means you need to allow for different return paths for faulted currents. So you want the DC fault current to go back to its source, and you want the AC system to go back to its source, preferably not to get confused and try and go back through each other's return circuits. Usually some compromise is required. So that's one of the things to worry about. I mentioned touch voltage, and that's minimised by getting a effective earthing and bonding system. Impact on other assets. So signalling system, for example. The DC and AC systems have different impacts and different ways of the impacting on the signalling system. So track circuits that might be used on a DC system may not be compatible with an AC system. And even though they're not on the railway, so you have an AC style track circuit on a DC railway, so 50 hertz, 60 hertz type track circuit, that will be interfered with probably by a 25 kV return current circuit. So you can't use that same technology on the AC railway. It also means we're at the interface point, you can't probably use that technology on the DC railway. So you've got to change the signaling system, track circuits and other things to make sure they're compatible. They usually refer to that as immunisation of the DC railway against the AC issues. Also telecom systems, same sort of issue, harmonics and return currents finding their way into telecommunication circuits is usually not good. So again, immunisation is normally required. A standard EN standard 50122.3 sets out the approaches you can use to manage the interfaces between AC and DC railways. So they're well defined, but the key message I want to leave with you people is that if we plan ahead for the two systems running together, we can generally find a solution that works, and usually they're related around space, insulation and bonding. If you get them right, you can come up with a solution. So it's always good to actually look at where this has happened in the past, interfaces I mean. So let's look at some practical situations where interfaces actually exist in the world at the moment. So I'll hand back to Stephen and we'll look at a few of those locations. So back to you, Stephen. Shall I move across to the first example?
Yeah, thank you, Andrew. Yes, please. Now this is an interesting one. It was built for the Commonwealth Games ahead of time, actually, and I was also working on this. So on the can you click forward, Andrew? On the left hand side of the picture, we have the Queensland Rail 25 kV AC, and on the right hand side we go code 750 volt DC. So you can see that it's actually quite challenging in terms of earthing and bonding. We got the station earthing and bonding, and then we got a 25 kV earthing and bonding, and then you got to manage the light rail as well. And the car park is actually fed from the station supply. So you can imagine that the earthing and bonding was quite challenging. So in the corridor, you know, we have to create sort of a like floating system if necessary not to bond to either system, so that you can't touch two systems and get zapped. And along the track, so you can see that the AC and DC are converging and running in parallel. And on the DC track, the light rail, stray current, DC stray current collection mat was installed, but not connected up. So all the conduits and everything are there. So if there's any issue, we can then connect it up to collect the DC stray current instead of letting it flows onto the AC railway. So myself and Jeff Russell read a paper in 2015, and right above on the screen there, you can actually have a look and see there's an awful lot of standards that we compiled that you can actually have a look at, and including the EN 5122 Part 3 that deals with an interface between AC and DC system next to each other. Okay, next slide, please. Now, this one I've shown before. I thought it was interesting that you actually have two systems running right next to each other, and especially going around a bend. And how would you stop a DC current not taking a shortcut through the AC system's running rails? You know, it's pretty impossible. And there'll be conductive coupling and so on everywhere, and also inductive coupling from the 50 Hz system onto the DC system as well. That would have been very challenging. Okay, next one. Now, I couldn't find the picture which I've been shown before. We had a 25 kV AC train on the sort of island platform, one on the right hand side, 25 kV AC and a 1500 volts DC metro system in Hong Kong, and they couldn't find a picture, so they have managed it quite well, the 25 kV AC and 1500 volt DC. They have lots of high-speed train from Kowloon, and you've got 1500 volt DC arriving there as well, 25 kV going to 44 destination in China. Okay, then next one. This one is my favorite. I designed the traction power system. I was the lead for traction power and earthing and bonding. I wrote the earthing and bonding strategy. Despite the strategy, and we still have civil engineer connecting our stationary bars to the tunnel mouth rebars as well, which we wanted to keep them isolated. And we do have a problem with interchange stations like Liverpool Street Station, and it was quite difficult to keep them apart. So and also because they're running, there's so many DC London Underground DC lines running in parallel to the Crossrail alignment, and London Underground would not accept any 25 kV system apart from auto transformer systems, because only then we can pull back our own 50 Hz leakage current. And any other system like rail return, it would have been flowing in their infrastructure and returning via their running rail and their tunnel, which is also bonded to their rails as well. And the top left-hand corner is the new Crossrail train. So the traction power has been tested in December 2018 and is ready, when waiting for the signaling and train control system software to be ready. So it looks like it's going to be delayed again due to COVID. And the bottom tube trains, and these are the new ones designed by Siemens, worth 94 units of 9-car trains, worth £1.5 billion. And there's also an option to build another 250 of these units. And you can see, and they have to be EMC and signaling compatible, and earthing and bonding compatible as well. So this is a very challenging one. And I think that is the end, isn't it, Andrew?
It is, Stephen. Thank you for
Yeah.
that.
Yeah. Thank you for
We'll
listening.
move on to some questions in a second, but just before we do so, as Stephen said, unfortunately, we couldn't find a really great image of the two systems in Hong Kong that run parallel. Stephen, you might like just to mention that the system in Hong Kong runs either side of the platform, so you'll have a 25 kV train on one side of the platform and a 1500 volt train on the other side of the platform.
Yeah, I have seen a picture. They're not side by side like that, but it's actually the 25 kV is actually on the other side of the island platform, and the idea is if you do have a fall of your overhead wires, it's not falling on your other system's track. So yeah, they have successfully managed two systems on the same station.
Thanks, Stephen. And I suspect the Melbourne system with the suburban rail loop, where it interfaces with the existing system, might do something like that and have one on one side, one on the other. So where there's interchange at the same level, same grade, that's the sort of thing.
Yeah.
Yeah. Okay.
Yeah.
So that's.
Andrew, I think we.
Yes, Stephen, go on.
Yeah. Yeah. In the picture you show has a location. So places like St. Mary's, you will have an interchange between DC and AC system. So there'll be some challenging, some challenges to be taken up by experts. In the UK, Network Rail expects the DC railways signalling track circuits to be immunized in both directions up to 2 kilometers. So if you're using 50 hertz track circuit, you will need to replace them with something else, maybe extra counter or something, and so on. So there'll be challenges ahead. So be prepared.
Okay, thank you, Stephen. I think we've got some time for some questions now. I'll ask Prath to try and moderate those.
No problem. I'll just show you, Andrew, the questions online. I think we've got 4 that have come through. So whilst that's loading, I guess I could ask a question. So I think this has been a debate that's going around for a long time, AC versus DC. I remember 10 years ago we were having this conversation when I was working as a project engineer for Novorail. I guess there's a lot of projects, greenfield projects that are happening at the moment, Metro's example. I think they're using DC. Have you been engaged by any of the new greenfield construction projects to do an analysis on whether you can install AC as opposed to DC, and why do you think the reason is that they've opted for DC?
Yeah, thanks, Prath. I'll probably ask Stephen to actually talk about some of the work we've done in Victoria to compare systems. Yeah, that's probably the best example at the moment. So Stephen, if you'd just like to give some background on this. Some of this is public knowledge and some of it's not so. So we'll have to be a bit careful the way we present it. But I'll let Stephen explain the work we did probably over 18 months ago now.
Okay. I've got to be very careful because of confidentiality. If you have powerful trains running on DC, if you want to let it do its job, it's going to be drawing a lot of high DC current. So as a result, you will have a lot of issues. For example, if you have a lot of highly sensitive medical equipment along the route, and you may interfere with their operation, and you got to somehow mitigate the electromagnetic field which interferes with them, and also the DC field for people wearing pacemaker as well, so which could affect them. And for the reason why you go for the AC is for the same power train, you draw only a fraction of the current. For example, a 5.5 megawatt train, crossroad train, only takes 220 amps at 25 kV, and volatile trains, if it's allowed to draw 3,200 amps, is already 4.8 megawatts. Yeah, so you can see that 220 amps versus 3,200 amps, that's a big difference. And if you want to do high speed, you certainly wouldn't want to go for a DC system, because you will need so many substations along the route, and drawing so much current, it wouldn't be very practical. So I actually did some calculation myself on high speed from Sydney to Canberra. You can achieve 1 hour journey time using 320 kilometer train in an hour. You go for AC quite effortlessly, and it doesn't use quite as much energy as DC because of the less losses.
Okay, thank you, Stephen, for that. We've got a few questions from the viewers at home. Stephen, I'm sure you can see it on your screen, but one of the questions is for both Stephen and Andrew. With SFC, is there active dynamic synchronization with any phase sequence? Getting quite technical here.
That doesn't sound like a question that's come from people that play with rails, but I'll touch Stephen. I'll let you answer that one. You have a go at it first.
No. Can I clarify what does it mean active? What?
Well, I am assuming that I'm not exactly sure. That question could mean a few things, but basically, perhaps we should just explain the operation of the SFCs. And Stephen, I'll let you jump in if there's anything I missed.
Yeah.
But basically, Stephen showed in his diagram there that we had parallel SFCs. So AC systems require a level of synchronization between sources. Otherwise, you get basically currents fighting each other. The voltage is opposing, which means that that's not a good thing. So as well. The SFCs have to operate in phase. So the voltage has to reach a peak at the same time. Now, there are different places in the network. The SFCs can be controlled independently. One could effectively be a slave, would set the frequency. One could be a master. What you can do with that system is then you can drive the power balance between the two SFCs. So you could have more power from one than the other, or you could run them at the same load basically. But because you've got two units so you can synchronize slightly differently, there's other reasons. You can set the voltage as well. You can actually control the power. So when it comes to synchronization, the 25 kV side does not have to be synchronized with the grid. It can be completely different. The whole point of a static frequency converter is to convert the frequency so there's independence between the incoming supply and the outgoing. The term frequency converter in the Australian context is a misnomer, as Stephen sort of said. It comes from the idea that the railways in the middle of Europe run at 16 and 16.7. Now the Germans are very precise now, not 16 2/3, it's 16.7 hertz, not 50 hertz. So they need that frequency conversion. They used to use big rotating machines. Power electronics has taken over, hence the term static frequency converter. It doesn't rotate, it's static, right? So hopefully that answers the question. But if whoever asked that question wants to hear more, we can. I
can probably add to that. With SFC, when you got different units, you can actually tune them to be in phase so that you don't need the neutral section. And also, you interestingly, you can actually route it up to an adjacent classic 25 kV system by tuning to its phase as well. So supposing the adjacent one is taking from, let's say, the A phase and B phase, you can actually tune your SFC to match that, and then you can do away with a neutral section. And with SFC, and supposing you got 3 units, one connected to 33 kV, another two, let's say 2 to 33 kV, the third one to 132 kV, and if you can buy in energy cheaper at the 132 kV, you can jack up the voltage and grab the load from the 33 kV, which you pay a lot more for the energy. So you can actually distribute the energy that way as well, and to save yourself some operating costs. And simply because you don't actually have a neutral section, so you can do that.
Okay,
so
thanks very much.
Not sure whether I answered the question.
I think you've covered it.
Yeah.
Another question from a viewer at home: how would an inline transition from DC to AC work? And then it's how long would the neutral section need to be to do that?
This is a system that is in place. In fact, I'll let Stephen talk to us in a second, because Stephen had experience with the transition on the original high-speed 1 service from the continent into the middle of London. Had that transition. I think it went back to a 750 volt system. There's a number of examples in the world. That was a overhead system to a contact rail system. The photo we showed of the Berlin system, I think, had a third rail 750 volt system. But yes, the question is quite right. There would need to be a section that's neutral. It's quite possible that the pantograph could run straight through, and that onboard the train there would be a control system controlled by probably trackside magnets or something similar, which would change the internal switching arrangements from whatever's required on one system, so it's the AC side with the transformer in series, to going bypassing the transformer, taking it out of circuit, and then going straight into whatever the traction equipment is. Because effectively, modern trains, the difference between DC and AC is just that transformer at the front end, different sort of circuit breaker, etc. So that's how it would go practically. So train approaches, traction power goes off, the switching happens inside the train, runs to the next section, power comes back again. Anything you'd like to add, Stephen?
Yeah, I can add to that. The old-fashioned British one is using APC magnet, APC automatic power control. So before and after the neutral section. So obviously how far back you position it depends on the line speed. So so when a train is approaching the APC, it will tell the train that you're approaching a neutral section. So it will then power down and try and get the current to 0 before it enters the neutral section. Any remaining current in the transformer will then get diverted to the arc when it enters the neutral section. The pantograph doesn't come down, the pantograph will just glide along, although the VCB vacuum circuit breaker on the transformer primary will open before it enters the neutral section. And when it comes out of the neutral section, the APC at the exit will tell the train you have now cleared it. So it will then close the VCB, and of course you have this whacking big massive transformer inrush into the power transformer of the train, which used to mess up the DC track circuits, and then it just carry on. So that's how it goes through a neutral section. I think some of the very short neutral section could be about, 10 meters, and depending on, I suppose, the speed and all that. And of course some of the new ones are using Belize instead of APC, and so that's a newer solution, and the same principle, and software base. So you got a transmitter telling the train that you're approaching neutral section. Some manufacturers seem to manage it better than others. It takes longer to get through the neutral section and power up again, but the conventional APC was very quick. Old technology, it worked. And on the Eurostar, originally running from Waterloo, it was actually 750 volt DC, and then of course when it joins the 25 kV AC, it has to go through for a floating section and interchange stations. So basically, it goes through no man's land, and the shoe gear will come up and coast through the dead section. All the current, of course, it goes through all the interface transformer and so on. And then when it's past it, the pantograph will pick up this 25 kV supply and carry on. And of course, that was removed because it was drawing so much current, it was tripping up the 50 Hertz track circuits. They actually have to increase the duration of detection before it says is an interference, and that didn't work very well. As then, of course, when the section 2 25 kV 2-ton 25 kV went all the way to St Pancras station, although the last section is actually a rail return system from the last transformer, that becomes all 25 kV. So no more DC AC interface. And the Belgian one, originally they had a 3000 volt DC. They have now converted to 25 kV AC as well. And so, you know, for higher speed and lower current, everyone is going for 25 kV AC. The Dutch 1500 volt DC has been converted to 25 kV AC as well. I think the Germans supported them because I think the Dutch port was actually more convenient for them instead of going through the very shallow Baltic Sea to get up to the open sea. So, so you can see that quite a few countries have converted their 3000 volt system, including Spain, to 25 kV AC. All high-speed ones are 25 kV AC. The very old Japanese one, very early one, there had been one which was DC. Then if you look at the history of it, all gone AC. Yeah, all high-speed one, almost all of them are using auto transformer systems because you can go longer distance, and you know, auto transformer. Although we said typically 10 kilometers, and the French put them at 12.5 kilometers, so you can effectively put a 15 if you want to, if your voltage doesn't sag too much in between. Yeah, so obviously the voltage would sag, a bit like your mother's washing line. When she put a prop on it, the washing line would still dip between the poles, and the auto transformer has that effect. It's like propping up poles, and you know, to stop the line sagging in voltage, you know. And it boosts the transformer. Of course, every boosted transformer location, the voltage would drop vertically. Yeah, so before long you run out of voltage. So if I were to design crossroad using booster transformer, I would need 2 feet feeding into the station, into the tunnels, and there'll be a neutral section in the middle. When I show the fireworks caused by a neutral section, the Hong Kong one, to the safety chap, he said, I'm not having that because of fire, risk of fire inside the tunnel. So I had to go for the auto transformer solution. And then when I proposed it, the French chap who was on the client side, he said, Stephen, you're mad. That is reserved for a high-speed line. I said, well, we have a high-capacity railway. Why don't we try that? And so before long, he was on my side. He was humming along the corridor, go green, go 80. Hence the motto on the last slide.
Okay, thanks, Stephen. We're running a bit out of time, but I think there's a lot of questions, which is good from the viewers at home. There's a couple that I can probably combine. So I'll ask 2 more questions. The first one is, the benefits of a 25 kV AC system over a DC system is known. However, what would you suggest you do to change the DC OLE system construction over an AC OLE system, taking into account that the AC system is lighter?
Okay, I'm going to run with this one. The next, I'm just going to move also, I think, incorporate a few outline of how New South Wales might transition and then can the network be converted? The approach goes something like this, and this is for foreseeing what we talk about in a full-blown presentation on this. But the first thing you got to do is pick a train that can run on both systems, because as you would probably appreciate, you can't buy a whole heap of trains ready for transition and have them sitting in a paddock. That's not going to work. So it's just not going to work economically. So you need to have a train that can run on both systems. That's the first thing to do. Before you start converting, you probably want to think ahead about what your system is going to be like, what your 25 kV system is going to be. If you're going to start that conversion process and do it over a period of time rather than shut a system down for weeks or months and then convert it, you're probably going to build insulation to start with into your 25 kV system, in your 1500 volt system, to be able to run at 25 kV. So you'll do some insulation coordination, thinking about what you need to put in. You make your insulators bigger. That will change your headspace and your arrangement. So you'll have to design a system that can run at 1500 volts with the bigger conductors, but can operate at 25 kV in the future. Right. You'll also then need to plan how you connect the new connections in and disconnect the old ones, and you'll need to do that quickly, obviously. So you can put in place that overhead standard and gradually transition the existing system to a new system. Now, the problem might arise that you need quite heavy, as this question asks, conductors for the DC system. Doesn't matter for the 25 kV system, you can leave it as it is. It's just that you're going to have a longer insulation length, etc. You're also going to have to set up your earthing and bonding so you can easily change it over. So remembering that the DC system won't have the rail directly connected to earth anywhere, whereas the AC system will. All your line side structures are probably connected back to the rail. That can be done fairly quickly, as you probably appreciate, but you need to set that up first. Immunisation of your signalling and auxiliary systems would have to be done, and you'd clearly be able to run a new signalling system with a DC system and convert it over, as long as you pick the right system. What do I miss there, Stephen? What else would you have to set up before you transitioned? Put some feeder stations in, of course, ready to go.
Yeah, we have it already. There are two very good examples. One is the Great Eastern Main Line. It went through so many changes. One of them was 1500 volts and eventually to a booster transformer system. Imagine from 1500 volt DC to 25 kV booster transformer system, and then it changed to auto transformer system. So that line has been like an experiment, because in the past it was DC. and when I spoke to the Dutch people about their conversion from 1500 volts to 25 kV, they were quite helpful actually. I lost contact. I didn't take it up on their offer to help us, and they were willing to share their knowledge on and some of the lesson learned, what to look out for and what pitfalls, and so no reason why we can't contact them again. So basically, the Great Eastern Main Line, I remember a lot of work was done in preparation, and then over was it long weekend, some of the things were switched over. Don't forget, when you convert to 25 kV AC, your insulator is going to be quite a bit bigger, longer, and your wires, you can use the same one for contact and catenary, and remove all your auxiliary wires on the pole because you don't need them anymore. And you may keep one as your, depending on what system you go for, if it's auto transformers feeders, and you can keep one for your minus 25 kV and one for your earth wire, because you need an area earth wire to basically your rails are earth, and it would be bonded to the rails and bonded to the structure to give you your distributed earthing system. And the earthing is, it doesn't have to be very low. In fact, each structure in the UK, when we measured it, it was depending on soil resistivity, it was ranging from something like 7 ohm to 10 ohm per structure. So you got something there, you know, and in 1 kilometer that's where you get your 1 ohm, which was specified by Network Rail anyway. So you know, you're not trying to get 1 ohm from each one, and you're trying to get a distributed. Why do we earth the rail? Because if we don't want the rail voltage to float above 60 volts. You allow up to 60 volts. So
don't give away all the secrets for the next presentation. We've got to leave some information for the next presentation. Yeah, how about we? Sorry to interrupt there, Stephen. How about we wrap it up there for this this question, and I'll hand back to Prath.
All right, thanks very much, Stephen and Andrew. That was a great presentation, and the amount of knowledge you both have is extraordinary. I mean, you pay consultants top dollar to answer some of those questions, so it was great. You just spilling it all out for free. But anyway, we'll have to have you back for part 2 of that. Again, thanks for sponsoring the event. The next event is in June, so make sure you come along to that. WSP will be the sponsor. Further information about what's going on in the PWI can be found on the website. I think some of the awards have started to open up as well, the Young Achiever Award, etc. So make sure to have a look at the website. And that will conclude the meeting. So thanks for joining us.